Hi, today we're going to talk about three periodic properties. So we ended the last video by talking about valence shell electrons, which are the electrons in the shell that has the highest principal quantum number. And because these are the electrons that interact with the outside environment, the electron configuration of your valence shell is going to determine the chemical properties of an element. Now, before we dive into these different periodic properties, we need to talk about a law of physics, which is Coulombs Law. And this is basically the law that talks about the force that is felt between two particles. And so, of course, there is an equation associated with this, and I'd like to talk through what each of these things mean. F here is the force between the two charged particles. This is a constant. If I were actually asking you to calculate the force, I would give you the constant, but you'll never actually have to do this math in Gen Chem. Q1 is the charge on particle 1, Q2 is the charge on particle 2, and then R here is the distance between two particles. You're going to square that. Now, an important note, if you have a positive charge on one particle and a negative charge on another particle, you're going to get a negative number for your force. Whereas if you have two charges that are the same, you're going to get a positive number for your force. That will tell you the direction the force is pushing. So a positive number means the particles are pushing away from each other. That's a repulsive force. A negative number means they are moving together, so that's an attractive force. Now, most people can't remember Coulombs Law off the top of your head, so I just tell people to approximate this as the force is going to be charges divided by distance. So we're going to keep coming back to that over and over. Now let's take Coulombs Law and let's put it in the context of an atom. So we need to think about the force that's holding that electron to the nucleus. And that's going to depend on the distance between the nucleus and the electron and the charge on the nucleus. Now you might say, why not the charge on the electron? Well, it does depend on that, but the charge on an electron is constant. Different nuclei have different charges. So the charge on the nucleus of a given element will be different from the charge on the nucleus of a different element. So we're really going to focus on the nuclear charge and the distance. Distance is pretty easy because we can approximate it with the principal quantum number n. The higher your n, the bigger your distance. And remember, we divide by distance when we're calculating the force. So the bigger your distance, the smaller the force will be. Likewise, if you have a small n, which means you're closer into the nucleus, you're going to have a small distance between the electron and the nucleus, and therefore you're going to have a large force holding the electron to the nucleus. So now let's talk about the charges. And we're going to look specifically at the element lithium, which has an electron configuration of 1s2, 2s1. So there's two electrons in the 1s shell, which I'm not showing here. And then there's that one valence electron, 2s1. Right now, what I'm going to do is make a statement and then I'm going to explain it. And that's basically that valence electrons don't feel the full charge of the nucleus. So in this case, what this is saying is that the force between our valence electron, which here is in the 2s shell, and the nucleus, which has a +3 charge, is not going to be as strong as if there were no electrons in that 1s shell. And the reason why is if an electron in the 1s shell is between the valence electron and the nucleus, it's going to interfere with that attraction between the valence electron and the nucleus. So you can imagine that the two electrons will repel each other if the core electron, as we call it, is between the valence electron and the nucleus. There will actually be a force pushing the electrons apart, which pushes the valence electron away from the nucleus. So you might ask, how do you know if that core electron will be between the nucleus and the valence electron? Well, you don't, because both of the electrons are moving pretty fast. But the point is that for a certain fraction of the time, one or the other of these two core electrons in the 1s shell will be between the 2s electron and the nucleus. This is a phenomenon we call shielding. Basically, any electron with a smaller principal quantum number will shield the valence electron from the nucleus. Other valence electrons don't shield that valence electron from the nucleus because they are not between the valence electron and the nucleus. So now I'm going to introduce a quantity that we call effective nuclear charge, abbreviated Z effective, Z sub EFF, which is the charge that the valence electrons actually feel attracting them to the nucleus. So there are a couple of different ways you can define effective nuclear charge mathematically. The effective nuclear charge is going to be the atomic number, Z, minus the number of core electrons, which are basically the number of electrons that are not in the valence shell. So there have been times when people have asked me, hey, if that's true, isn't the effective nuclear charge the number of valence electrons? And that is only true if you have a neutral atom. If you're talking about an ion, which we will be talking about very soon, then that is not the case. So the first equation is the most correct equation, but if you're talking about a neutral atom, you can shortcut with the second equation. All right, so we're going to look at effective nuclear charge as we go across the periodic table. So I'm going to start with lithium. The atomic number of lithium is 3. And how many core electrons does it have? Well, this is everything that's not in the valence shell. So it has 2 core electrons. So it's 3 minus 2. That gives it an effective nuclear charge of 1. Beryllium has an atomic number of 4. Its core electrons are still the 1s2 electrons. So 4 minus 2 is 2. And you can see with beryllium, it's still going to have 2 core electrons. So 5 minus 2 is 3. For carbon, the same. 6 minus 2 is 4. Nitrogen, 7 minus 2 is 5. Oxygen, 8 minus 2 core electrons is 6. Fluorine, 9 minus 2 core electrons is 7. Neon, 10 minus 2 electrons is 8. And then we get to sodium, but notice that with sodium, our valence electron is the 3s1 electron. And so all of these here are core electrons, so there's actually 10 of them. So sodium has an atomic number of 11, minus 10 core electrons gives us 1. So what's going to happen in general is as you go across the periodic table, Z effective is going to increase. Now you'll notice it says generally, and that's because transition metals are weird. And weird things do happen with transition metals when we're talking about periodic properties. So quick summary of what we've just talked about. The higher the value of the principal quantum number, the bigger the distance between valence electrons and the nucleus, and therefore the weaker the force holding an electron to the nucleus. The higher the value of the effective nuclear charge, the stronger the force holding an electron to the nucleus, because that's basically the charge that you put in for Q1 in Coulombs Law. So now we're going to talk about 3 different properties: atomic size, ionization energy, and electron affinity. And you will notice that what we have just talked about in terms of distance and charges is going to apply to all 3 of these periodic properties. The first periodic property is atomic size. And let's think about what determines the size of an atom. Remember, the nucleus is just a teeny tiny part in the middle of the atom, and most of the volume of the atom is made up of electrons. So really, atomic size is based on the distance from the nucleus to the valence electrons. Okay, well, if you think about the distance, the stronger the nucleus pulls on those valence electrons, the closer the valence electrons will be to the nucleus. So what we're looking for is strong forces mean smaller atoms, weak forces mean larger atoms. So again, as your principal quantum number increases, the distance from the nucleus of the valence electrons is going to get larger, and that means the force is going to be weaker. So if you have an element that has valence shell being number 2, it's going to be smaller than something that has a valence shell with n equals 3. So that's distance, and then we also have to think of charges. So let's think of 2 elements within the same period. So they have the same valence shell. As the effective nuclear charge increases, those electrons are going to be pulled in more strongly towards the nucleus, and that will make the atomic size smaller. So you can have something with a +2 effective nuclear charge, and you can have something that has a +4 effective nuclear charge, and the +4 will actually be just a little bit smaller. If you look at the periodic table, what you're going to notice is that the higher your principal quantum number, the larger your radius is going to be, whereas the lower your principal quantum number, the smaller your radius would be. And that tells us that the smallest radii are going to be at the top of the periodic table. So now let's think about effective nuclear charge. The higher your effective nuclear charge, the more the electrons get pulled on, and the smaller your radius will be. And we just saw from that little exercise we did that as you go across the periodic table from left to right, your effective nuclear charge gets higher. So the radius is actually going to decrease as you go this way across the periodic table. So let's look at some actual atomic radii. So on this graph, atomic number is on the x-axis, and the covalent radius in angstroms, which is 10 to the minus 10 meters, is on the y-axis. Let's look at what happens as we move along the periodic table. So here's hydrogen, and here's helium, which goes down a little bit. Remember, the effective nuclear charge is higher, so it's going to give it a slightly smaller atomic radius. And then next we go to lithium, and you see that the radius goes up. Why is that? That's because these are in n equals 1, lithium is in n equals 2. All of these, in fact, are in n equals 2, but you can see that as we go across n equals 2, we see the covalent radius decrease. So here's lithium, here's beryllium, here's boron, here's carbon, nitrogen, oxygen, fluorine, neon. And then neon is the very end of valence shell n equals 2. So the next set of elements are in n equals 3. And you can see sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. You could see here that after a while they don't decrease by much, but they do decrease noticeably across a period. And then obviously once you get past argon, then you're in n equals 4. And of course it continues past this. I'm not going to show that on the graph because things get funky when you get into the transition metals, as always. And so here's potassium and here's calcium. Our next periodic property is what we call ionization energy, which is the amount of energy it takes to remove an electron from an atom. So here I have a diagram that shows beryllium, which is element 4, and it has 4 electrons when it's neutral. 2 of those are going to be in 1s. Those are the core electrons. 2 of those are going to be in 2s. So you can imagine that you can take these electrons off. And when you do that, you always remove the outermost electrons first. So if you take away the first electron, we would call that the first ionization energy. If you keep taking electrons off, we're going to call it the second ionization energy, the third ionization energy, and then of course the fourth ionization energy. And you can imagine that a larger element could have even more ionization energies. But let's go back to our original neutral atom. When you try taking an electron off, the nucleus is going to pull that electron back towards it. So if you want to completely remove the electron from the nucleus, what you're going to have to do is you're going to have to pull with a force that is greater than the force that's holding the electron to the nucleus. So the more strongly that nucleus is holding on to the valence electron, the higher the ionization energy is going to be. And so if you think about it, this is going to work like all other periodic properties where we have to think about that force between the electron and the nucleus. How will the ionization energy change within groups and going across periods? Well, the higher your principal quantum number, the weaker the force will be because the farther those valence electrons will be from the nucleus. So the low ionization energies are at the bottom of the periodic table. The high ionization energies are at the top of the periodic table. Going across a period, your effective nuclear force is increasing, which means the nucleus will hold onto those valence electrons more strongly. So the higher your effective nuclear force, the higher your ionization energy is going to be. So we should expect to see stronger ionization energies as we move right across the periodic table. So let's look at the ionization energies, and you'll notice this isn't quite as obvious a trend as the atomic radius, and that's why we always start with radius. Oh, here's hydrogen and here's helium. Because helium has a higher effective nuclear charge, we do expect it to have a higher ionization energy. Next is lithium. Now we do expect lithium to drop because, of course, it is in n equals 2, so it's farther away from the nucleus. It should be easier to pull off. Beryllium has a higher effective nuclear charge, therefore it should have a higher ionization energy. Now what about boron? Why does that go down? Well, the answer is if you pop an electron off of boron, it ends up with a full S shell, which, remember, is more stable than having a full S shell plus 1. So it's actually more stable to get rid of that electron. That doesn't mean you don't have to put energy into the atom to pull the electron off because, of course, the nucleus is still holding on to it. So after that, you can see that it's going to increase as we go to carbon, as we go to nitrogen. Then it goes down again when we get to oxygen. Now, why is that? Well, if oxygen loses an electron, it will end up with a half-full p shell. And of course, remember, that is not quite as good as having a full shell, but half full is a fairly stable electron configuration. And then, of course, we can go to fluorine, neon, and then we're going to n equals 3, so it drops quite a bit. Sodium, magnesium, down again for aluminum because losing an electron will give us a full 3s shell. Silicon, phosphorus, down a tiny bit for sulfur because that would again put us at the half full p shell. And then chlorine, argon, potassium, n equals 4, drops down even more, and then calcium. The final periodic property we're going to talk about in this video is electron affinity, which is basically the opposite of ionization energy because it's how much energy does it take to push an electron onto an atom. So let's go back to beryllium. I'm going to pop in our 3 electrons. So basically what we're doing is we're trying to push that extra electron into the 2s shell to give lithium 1s2, 2s2 electron configuration. This is not a natural state of affairs, and so what you have to do is you have to look at how strongly can that nucleus hold on to one more electron. Now, how will that change within groups and moving across periods? Well, the farther that electron is out from the nucleus, the weaker the force that's holding it to the nucleus. So once again, we're going to expect the electron affinity to be higher at the top of the periodic table and weaker at the bottom of the periodic table. Now, when we're talking about going across a period, remember effective nuclear charge increases as we go across the period, and The stronger the charge, the more likely something is to be able to hold on to an extra electron. And so we will also expect to see a stronger electron affinity as we get to this side of the periodic table. There is an exception to that last rule, and that is the noble gases. So what I'm going to do is I'm going to look at 3 different elements: oxygen, fluorine, and neon. And I've put here the electron configurations of those neutral elements. So oxygen goes up through 2p4, fluorine 2p5, and neon 2p6. So now let's look at what happens if we add an electron to each of those elements. Oxygen will become 1s2, 2s2, 2p5. Fluorine will become 1s2, 2s2, 2p6. If we add an extra electron to neon, we can't put it in the 2p like we did with oxygen and fluorine. So where is it going to have to go? It's going to have to go in the 3s shell. And so now you can see that when you start with an electron configuration ending in p6, there is nowhere for that extra electron to go but in the next shell up. And because it's the next shell up, it's further away from the nucleus, and it's harder for the nucleus to hold on to that electron. So we should expect to see noble gases having a very low electron affinity. So here is a graph. You can see that this graph is even more funky than the ionization energy graph. So we can put an electron on hydrogen. Helium really doesn't want one. We can put one on lithium. Beryllium also doesn't want one, and if you think about that, that's because beryllium has a full s shell. You have to put the electron in a p shell by itself to give it an extra. Okay, boron can hold on to one a little better. Carbon can hold on to one. Nitrogen, it goes down. Why does it go down? Because nitrogen has a half full p shell. If you give it an extra one, it no longer has that half full p shell. Right? Oxygen wants one, fluorine wants one, neon really doesn't want one. Okay, so you can see how this changes, and it is, again, not as clear a trend as atomic radius, but it is predictable. One of the most important things you can take away from this, which is really going to drive a lot of what we do in the next few weeks, is thinking about the trends with noble gases. Noble gases have the highest ionization energies, so more than any other element, they don't want to lose electrons. Noble gases also have the lowest electron affinities, so they also don't want to gain electrons. So what does this mean? If they don't want to lose electrons and they don't want to gain electrons, that means they have the most stable electron configurations. And so what we're going to see moving forward is that other elements are going to try to achieve noble gas electron configurations somehow or another. This introduction to periodic properties shows you that they are predictable based on what we know about electron configurations and what's stable in an electron configuration, and also based on what we know of Coulombs Law. I hope this was helpful, and I look forward to seeing you again soon.